Okay. So a few announcements to start. So first of all, apparently someone in the college surveyed all of you about this class and probably all of your classes, at least within the College of Engineering. I wish they had told me. I could have encouraged people to fill it out, as it was about half the class filled it out. I just feel like I'm entitled to know when stuff like this happens. Like as the instructor of the class, I feel like I should know what's going on. So anyway, it happened, and they sent me the results. So I went through it pretty carefully. So thanks to everyone who filled it out. There were a number of positive comments about the class. I will not share those with you, unless you really want me to. The critical there were a few critical things that jumped out at me. So office hours. So I do try to be as helpful as I can in office hours in terms of like showing you how to do homework and stuff. Umair has the same approach. I gather from the comments that for people who can't make office hours, they feel like this puts them at a major disadvantage. So if that's you, so if you cannot make any of our office hours, then please just send me your schedule. We'll work something out. I know it's a bit late now. We only have like 2 full weeks left of the semester at this point, but we'll do what we can. So anyway, if that's you, just email me what your class schedule is or your schedule when you're free in a typical week, and then we can add an hour or something to try to accommodate that. Inclusiveness, so everyone who completed the survey said that they felt included, but one person indicated that they thought there was someone else in the class who did not feel included on multiple occurrences, it said. So anyway, if that's you, or if you don't feel included, or if you think you know someone who may not feel included, then please share with me what I can do, what Umair and I can do to help fix that. I do my best. There's some things that I know we're not perfect in this regard. For instance, a very small example, I tend to use baseball terminology. It's just my manner of speaking. So like right off the bat, we're going to X. I think last time I noticed I said a couple of bits were on deck. Input bits were on deck, right? So it's just the way I talk. I was into baseball as a kid. I know if you did not grow up in the U.S., or just weren't into baseball, that might seem like kind of foreign language to you. So anyway, usually I say that, and like the moment it comes out of my mouth, it's like, okay, I shouldn't have used that terminology, but it's hard to change your way of speaking. So anyway, if there's things we can do that would make people feel more included, do share them with me. You can. I'm happy to chat about it. If you want to just come and chat, you can talk to Umair if you're more comfortable with that. If you want to just like slip an anonymous note under my door, that works too. Whatever's good for you. The chapter notes, yes, I know I'm behind on those. I apologize. It's not that I'm holding them back, it's that they're not done. Okay, I got to write these things, and it takes a huge amount of time to do that and polish them and so on. So I work as quickly as I can, but obviously the lectures take priority, and we got to stay on top of the labs and stuff, so it takes priority. Anyway, so that's the main kind of constructive criticism comments from the survey that I got. Anyway, if you have other comments, I'm always happy to hear them. Continuous quality improvement, that's our motto at ECE4670, 5670. Okay, so let's see with labs and homework. So lab 4 due next week, right? Next Friday, no lates, okay? Because 5 p.m. Friday, we're gonna start running these things so that we can get, I was about to say teed up for the voting, so we can get prepared for the voting on the following Tuesday. So I recommend not saving this to like the night before. It does take a little bit. Ultimately, the code, your final code base, is not really that long, but it can take a little bit of time to kind of figure out, what you're doing. So I'd recommend starting early. A couple of tips just to get started. One thing you can do is just have an encoder that just sends an impulse through, and then design a decoder that just finds the start of the impulse. Just do the triggering thing that we talked about. Start with that. Or put the ComCloud aside and just build an encoder that just works with an identity channel. So just run the decoder directly on the encoder's .wav file output. Okay, those are a couple ways you can kind of get off the ground if you're not sure where to start. We have a short homework due tomorrow, right? And I have office hours after class today. If you want to chat about that, or inclusiveness, or baseball, or whatever. I have to. They kind of sprung a one-off meeting on me that I need to attend from 4 to 5. So Umair will cover my office hours from 4 to 5 in his usual office just around the corner from me. After class until 4, I'm happy to chat. That's all I have. Any questions? Yes.
Would it be a problem if we're like
It depends what you mean by problem. I mean, so, I guess if we do the vote, we don't have to do the voting on the Tuesday before Thanksgiving. So let's just do a quick show of hands. So, who plans to be here? Be honest, please. Who plans to be here the lecture the Tuesday before Thanksgiving? Okay, that's full employment. So, so I'd like to do it then. I think it's a good topic for Thanksgiving week, and it would kind of keep us on schedule more or less. The only hang-up is, like, if of the people who are not going to be here, like, obviously if I was otherwise going to select your standard for one that's presented, then like that's going to be no-go, right? So so that's the hazard. In terms of voting, we don't need everyone here to vote. I mean, it's a problem if it's just the two teams themselves and no one else, then that's kind of a problem. But I mean, as long as we have a reasonable, like a quorum, that's fine. So so I guess, like, if you are not able to present and we therefore do not consider your design as a possible standard for voting, do you consider that to be a problem? I mean, I don't, but that's more maybe a concern for you. Yeah. I mean, I understand. There's two sides of this, right? I can understand on the one hand, like, people need to travel, and sometimes, you get the flights when you get the flights, and so on. From my perspective, on the other hand, though, like, Tuesday is a legitimate lecture, and the university is open, and so it's a bit of a slippery slope when we start saying, okay, this class, although it's an official class, we can't really do anything. We can't do stuff we'd otherwise do because people will not be here. I mean, we need to treat it. If it's university is open, So, so we'll let's plan on doing it the Tuesday before Thanksgiving, then the voting, and that's partly why the reason I said no lates on on Lab 4, because we'll start running them as soon as we can, go through the standards as soon as we can, and then we'll need a little bit of time to turn this around, because we might go to people and invite them to present and then say I'm not here, and then we should go to another group and so on. So we need some time to kind of negotiate all that. Yeah. Okay, other questions? Good? All right. So today I'd like to finish talking about convolutional codes, and with luck we'll start talking about wireless. If not, wireless will be our topic for next week and thereafter. So we have about roughly one lecture worth of material for coding and convolutional codes left, and then wireless is like our last unit for the semester. Okay, so we're in coding. Coding is basically a question of, or a study of how you map data bits into channel inputs in a way that allows you to, like, optimally recover from the noise. And we studied that first for the binary erasure channel, and I think, like, the phenomena there is particularly transparent in the binary erasure channel case, so it's worthwhile to do it in that channel first. A few of the lessons that popped out of that, one was you got to mix the bits, okay, which is a bit counterintuitive given what we did earlier in the class. You got to mix the bits. The mixing should be sort of erratic and long range. Okay, it shouldn't be like a very consistent, predictable mixing, repetitive mixing of kind of bits that are close to each other in the string. You got to kind of mix bits from all around the string. And there may be other lessons you can draw too, but those are maybe the two ones. Also, decoding is usually more complicated than encoding. So those are 3 lessons you can draw from that simple channel. But ultimately, we don't want to communicate over a simple channel like that. We want to communicate over ComCloud or wireless channels or whatnot. So there are a few ways of extending that binary erasure channel story to more general channels. I'll show you one. This is not the only way of doing it, but it's a particularly intuitive way, especially for people with an electrical engineering background, because it's sort of like filter-based. Okay, and this is also what's done in Wi-Fi. Actually, there are various coding schemes in Wi-Fi. This is one of them. This one's been there for a while. Some of the other ones are more recent. Okay, so the convolutional code, like a general convolutional code, is really a bank of shift registers with a bunch of output taps. So I've drawn, instead of drawing the generic picture here, I just drew one example that we used last time. So in general, you might have several of these shift registers, and the bits that you're trying to send, you would in that case like divide those bits into several substreams, and each substream kind of drives a separate shift register. I'm drawing the case where you have just one shift register. So the bits come in, and you start with like a 00, just all the delay elements have a 0 stored in them, and then like at each clock tick, you just sort of like push a bit out. All the bits in the shift register shift over by one more input bit gets inserted. Okay, and then this is mod 2 arithmetic, so this is basically taking the XOR of the bit in this flip-flop and the input bit, and this is taking the XOR of the bits in these 2 flip-flops. Okay, so for each bit that you feed in, like 2 pop out. Okay, and you do this for your entire stream. Like I said, you initialize with a 0 state, Okay, and you always, given your input string, you always pad enough zeros on the end, okay, so that you return to the all zero state. So in this case, you would, if you're trying to send 3 bits, you actually send 5 because you take the 3 data bits you're sending and then you append 2 zeros. No matter what the data is, even if it's all zeros to begin with, you append 2 zeros so that you're guaranteed that the system returns to the all zero state when you're done, okay? So here's one example I worked out. This is actually a different example from what I did on Tuesday, but you can work this one out too. So if this is the input string, okay, you start with all zeros. If you just implement this shift register, you'll get 10 bits out. Okay, so the first bit goes through. You have to actually flip this, as we discussed last time, right? But since it's 101, it doesn't matter whether it's flipped or not. So 1 bit goes in and you get 2 bits out, and 1 bit gets in, 2 bits out, 1 bit in, 2 bits out, and then you have the 2 zeros that you feed in at the end. Those give you 4 more outputs. Okay, so 3 bits gets mapped to 10 here. The rate of this particular convolutional code is defined to be a half because it's kind of in the over the long term you get 1 bit in and 2 bits out. So we define that to be a half, and it's not quite half here. It's 3 to 10 or 3 divided by 10 because of the edge effect from those extra zeros. Okay, so encoding is pretty simple. Okay, encoding, is very fast, conceptually very, very simple. You're just implementing this shift register. As is often the case with coding, okay, the work is really at the decoder side. So the decoder would, if it got this bit string, okay, then it could sort of reverse engineer like what the input had to be in order to give rise to that output. The trouble is you're going to send it through a channel that's not going to allow you to recover this exactly. Like for instance, you might have a bit flipping channel, the binary symmetric channel that flips some of the bits. Okay, and then the string you get here doesn't correspond to like any valid sequence of outputs here for any input. Okay, so then you got to decide what to do. You got to find one that's somehow the most plausible or most likely given this. Okay, so the way we do this, first of all, observe since the input stream is driving these shift registers, and the shift registers comprise the state. Okay, if the decoder can just figure out what the transitions of the states were, like the evolution of the state, then it would know what the input string was, right? So it knows it starts in 00. It knows it ends in 00. Okay, and if you can just figure out like what states it moves between when it's going from 00 back to 00, you can then reverse back out what the input is, right? So for that, it's helpful to draw a state transition diagram. Okay, so that convolutional encoder has 4 states, right? 2 bits. So it can be 00, 01, 10, 11. Okay, and then in each state there are 2 possible transitions because you can input a 1, or you can input so you can input a 1, you can input a 0. Okay, and the format here is to the left of the slash is the next input bit. Okay, the arrow tells you which state you go to next, and this is the 2 output bits that you peel off here and here. So the left one is output 0, and the right one is output 1. Okay, so if you're in state 00, and the next input is a 0, then when you shift, this 0 will fall off. This 0 will replace. Okay, this 0 will fall off. That one will move to the right. This one will replace that one. So you end up in state 00 again, right? And then you're going to output 00 because if everything's 0 here, if this is all 0, 0, 0, then you're going to get 0, 0, right? Okay? And you can do all these combinations here, right? So if you have state 1, 1 and you input a 1, right, then you're going to stay in state 1, 1. Okay? And you're going to have 1s all the way through here, so both of these XORs are going to be 0, right? Okay. So let's suppose the encoder and decoder agree how long the string is, just like in your lab 4. So let's suppose everyone knows we're sending 3 bits, and everyone knows there's going to be 2 bits of 0 padding. Okay, so there's going to be like 5 states total, right? And the encoder and decoder both know everything starts in 00. The decoder knows that the encoder starts here, okay? And for this input string, okay, the transition is going to, that input string corresponds with a certain trajectory through this diagram, right? So it starts here, it gets an input of a 1, that takes me here, then gets a 0, that goes here, 1, takes me back here, right? And then you have 2 zeros then, right? So 0, 0, right? Okay, so this particular input string here corresponds to that particular trajectory, sample path, on this state transition diagram. And there are 8 total valid paths that start here, take you back to here in 5 steps. Those 8 correspond to the 8 different strings here. Okay, so on some level, the decoder is trying to figure out what path the encoder followed. It know it started here, it know it ended here, it know how many steps it took. Okay, it's trying to figure out what path it followed. Okay, so for that, it's helpful to just expand this thing out over time. Okay, so here's the same, essentially the same information, just drawn kind of over time. Okay, so we know the encoder starts at 0, 0. Out of state 0, 0, there are two possible transitions. Okay, if it remained in 0, 0, again, there are two possible transitions. If it's in 1, 0, there are two possible transitions, and the thing, kind of fans out that way. Okay. So another way of looking at it is the decoder knows we started here and ended here. So 5 transitions total. Okay, and every possible data string, namely this, okay, corresponds to one valid path from here to here. Okay, so the 1, 0, 1 string, that would be, there's a 1 there, 1, 0, 1, right? And then 0, 0, right? So the 1, 0, 1 string corresponds to that path through this trellis, and there are 8 total valid paths. Okay, notice that like you actually, I mean, I drew this up here, but you can't end up here, right? Because the last 2 bits are 0, so it's going to take you down to there. Okay, and I color coded just to keep track which arrow comes from which state. That's all the colors are doing. Okay, otherwise there's just so many lines, it's hard to keep track of which numbers associated with which arrow. Okay, so any questions about this? I think this is where we ended last time. Okay, so the decoder wants to figure out what path we followed given the information available to it. Okay, it knows that as we started there and ended here. Okay, so to answer this question, we need to specify the channel, right? So we know what goes into the channel, namely this bit string. Okay, we need to specify what comes out in order to, say, solve a map detection problem. Okay, so let's suppose the channel is a binary symmetric channel. I think I introduced this acronym last time, binary symmetric channel. So it just flips bits with probability epsilon. So it's like the binary erasure channel, but it's maybe more along the lines of what you'd expect a priori. Okay, so you feed in a bit, and it flips it with probability epsilon and leaves it alone with probability epsilon. Okay. Okay, so let's create some notation here. So let U be the data bits that we want to send. X be the input to the channel. And this is equivalent to the output of the convolutional encoder. Okay, so that's this. It's the bit string that goes into the channel. Okay, and then Y, output of the channel. Okay, so you have your data bits, you feed that in the convolutional encoder, you get like a longer string, X. You feed it through the BSC, it flips some of the bits, you get Y. Okay, so the decoder wants to guess U from Y, right? So we're going to do map detection here. It turns out it's a lot easier to solve at least write out, it's just easier like notationally to write out the map problem if you try to guess X from Y rather than Y, or U from Y. Okay, the reason is that U and X are the same dimension, whereas U is smaller, right? Like here's an example. So this U maps to this X, and then you pass this through the channel and it flips some of the bits, you get another vector of the same length. Okay, but U and Y are the same length and they're very closely related through the binary symmetric channel distribution, whereas U to Y is got kind of a funkier relation. Okay, so it's a lot easier to detect X from Y, and then there's sort of an implicit step after that. And once you have a guess for X, then you just map that to U. We're assuming the channel, or the convolutional encoder is invertible. So if you have an X, you can get a U from it. Okay, so there's that extra step there. Okay, so let's do then the map detector of U not u, that was the whole point, of x from y. Okay, so I guess for x, okay, argmax over x, py given x, and then times the marginal of x, right? That's just the map rule, right? Okay. So, let's call n maybe the length of both x and y. So observe that only certain strings of length n are valid strings for x, right? Because x is the output of the convolutional encoder when you feed in data bits, right? So the x that comes out of the convolutional encoder must correspond to some path through this trellis, right? It could be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's one possibility. It could be another x could be 1, 0, 0, 1, 1, 1, 0, 0, 0, 0. Okay. But in this example, there are only 8 possibilities for x, and the x string is length 10, right? It's like 2, 4, 6, 8, 10, right? So x is length 10, but there are only 8 possibilities, only 3 bits, right? So not every string of length 10 is a possible valid x, right? So for a lot of x's over here, when you plug them in here, you're going to get 0. They can't happen, okay? So, but any x that corresponds to a path in the trellis could happen. Every x that corresponds to a path in the trellis are all going to be equally likely, assuming u is equally likely. Let's assume these are I d Bernoulli half. Okay, so essentially the x is uniform, but it's not uniform over the set of all possible x's. It's uniform over the set of valid paths through the trellis. Okay, so maybe just put this as an addendum here. So this is 0 if x does not correspond to a path through the trellis. And it's uniform over all x's that do. Okay. So in a sense, I can just, when I write argmax, I can just restrict the maximization to be those x's that correspond to paths in the trellis. Okay, and then over that set of x, this is always constant, so I can just drop it, and I have just the channel law left. So x such that x corresponds to a valid path through the trellis. Okay, so we're just left with this problem, right? Okay, the point is this is like, in our 3, a case where u is 3 bits and n was 10, like this is 1 over 8 if x corresponds to a valid path through the trellis, and it's 0 otherwise. Okay, so if you just restrict the maximization to be those x's that correspond to valid paths through the trellis, then this is fixed at 1 over 8. Okay, it doesn't depend on x anymore, so you can just drop it. Okay, what can we say about this for the binary symmetric channel? So first definition. Okay, so given 2 binary strings x and y, we'll define d of x, y, like the distance between them, to be the number of bits in which they differ. I'll say number of positions. It's maybe more accurate. In which x and y differ. Okay, so in terms of that notation, I can write down a formula for the conditional PMF of the channel. Okay, so if I feed in a particular x, the chance I get a particular y, okay, is going to be epsilon raised to the power number of bits in which these two strings are different. 1 minus epsilon, n minus that. Here, n is the length of both x and y. Right? Okay, so let me pull a factor of 1 minus epsilon to the power n out front. And I have epsilon over 1 minus epsilon. That whole thing raised to the power d xy. We call this the Hamming distance, by the way. It's like a notion of distance in the set of binary strings. Okay. So if we plug that in, I'm going to save the trellis. Okay, I'm going to search over all x's that are valid paths through the trellis. And then I have, if I just want to find the x that maximizes this, I don't care about the 1 minus epsilon to the power n in front. That doesn't depend on x. So you just have epsilon over 1 minus epsilon raised to the power d x y, right? Okay, so if epsilon's less than a half, okay, which is like the usual case, the interesting case, right? This is the case where the channel tends to not flip bits. Okay, then this factor is less than 1. Okay, so you maximize this by minimizing the distance. Okay, so you want to find the x string that's closest to the y string and is a valid path. Actually, I guess I should put the random variable y here. We've observed the channel output y. Let's make that capital. And then I want to search over all x's like this. That's it. Okay, and if epsilon happens to be bigger than a half, okay, then this thing's bigger than 1. So in that case, you maximize this by finding the x that maximizes this. So find the x that's farthest from y. Okay, in practice, if epsilon's bigger than 1, you would just like relabel 0 and 1 at the decoder, right? Like you just got the labeling wrong. Okay, so we can just assume epsilon's less than a half. Okay, so the way to think about this is that, every valid path through this trellis gives you a string of length 10 in this example. You've observed a string of length 10 from the channel output, so just find the path that gives you a string of length 10 that's closest in Hamming distance to the channel output. Okay, and that is the maximum likelihood guess for x, and it's also the map guess for x. Okay. All right. So so in a simple example like this, a small example, you could do this by hand, I guess, right? You could, given a string of 10 bits, you could just enumerate all 8 paths, and for each one, compute its distance from y, and then pick the shortest one. It's not going to scale very well, though, right? Because the number of paths, if u is k bits, if u is like k dimensional, okay, then how many paths through the trellis do I have? How many? Sorry, 2 to the k, right? Each u string corresponds to a different path through the trellis. Okay, so as I send longer and longer strings, okay, I've got more and more paths, and I send longer and longer strings. Of course, this thing's just going to keep growing this way, and so you get an exponential blow up in the number of paths. So just enumerating all these paths, and then just testing each one and see how far the string it gives you is from the receive string is not going to work. So we need a way of scaling this up. So luckily there's an efficient algorithm for doing this. And the way it works is as follows. So suppose you get a particular, so first of all, okay, two things. Let's index this as like time or stage or something. We'll call it t equals 0, t equals 1, t equals 2, 3, 4, 5. Okay, so that's one thing. Okay. Now, in terms of finding the, let me erase this thing on the top. So in terms of finding the path that's closest to y, you can think about that as follows. So suppose your y string was like, I don't know, 1, 0, 0, 0, 1. It doesn't really matter. I'm just going to draw arbitrary stuff here. Okay. So what you can do is for each edge, okay, that corresponds to a particular pair of x bits. Okay, you can compare that to y. Okay, and then just label that that edge with how many bits are different. Okay, so in this case we have 1 bit different. In this case we have 0 bits that are different, right? Here this has 0 bits that are different. This has 1. This has 1. That has 2, right? So you can do it all the way through. Okay, and then for any particular path that you have in mind, okay, its Hamming distance from y you can obtain by just adding these little distances on each of the edges, right? Okay. So one way of thinking about it is, at that point you can kind of just think about dropping all this information, and all you do is you have a trellis with weights on it or costs on it, and you want to find the path through the trellis that accumulates the minimum cost as it moves from one side to the other. Okay. That's essentially what the problem is, and there's an efficient algorithm for that. It's called the Viterbi algorithm. Okay, so Andrew Viterbi is an electrical engineer, and he taught at UCLA, I think, and UC San Diego, and then he started companies. He started a company called Linkabit, which is, I think, kind of a defense contractor. It probably doesn't exist anymore. I'm almost sure it doesn't exist anymore. After that, he started a company called Qualcomm, that you might have heard of. His co-founder in co-founding Qualcomm was someone named Irwin Jacobs. Irwin Jacobs was an undergraduate alum from this department, ECE at Cornell. I'm not sure, his work on this algorithm predates Qualcomm by quite a bit. Anybody know anybody at USC? Do you have friends that go to USC engineering? Yeah? You know the name of the engineering college at USC? It's the Viterbi School of Engineering, yes, exactly. So it's the same guy. So, okay, so this is an algorithm. So the input is a trellis with costs or rewards, essentially a number on each edge. Okay, so the Viterbi algorithm is not going to pay attention to, it's actually not going to pay attention to, the labeling of these states. It's not going to pay attention to what these inputs are, these outputs are. It's just going to look at the weights. It's just going to try to find the path from start to end that accumulates the minimum weight as you pass through. Okay, and I guess, so the input is that, and also start and end states. Okay, and the output is a minimum cost, or if you're doing rewards, a max reward. Path through the trellis. From start to end. Okay, so I'll show you I'll write down the algorithm. We'll do an example. The algorithm is not, I mean, it's not that complicated, but it's not exactly the first thing that you might think to try. So I think if you're to develop your own algorithm for this, you might say, well, okay, we're going to start here, and then there's like one or two possible paths I can take, right? And this one has no errors, and that one has one. So, and I want the lowest cost path. So this is cost 0, cost 1. So maybe I should kind of favor that one somehow, and then kind of explore out here. That doesn't work to try to do it that way. But it does work if you think about fan, if you're moving left to right, if you look at kind of like comparing fan-in possibilities instead of fan-out possibilities, it does work. Okay? Or if you move right to left, then you could do fan-in instead of fan-out. Anyway, it's maybe not like the first idea that pops in your head, but it's not too complicated nonetheless. Okay, so here's the algorithm. So you initialize the start state, with cost or reward 0. And let's initialize, let me write initialize t to be 0. Okay, we'll set up a loop. Okay. So increment t, so kind of look at one stage to the right from where you were before. T is sort of the time index here. Okay, so kind of advance one step to the right from where you were before. Step 4, for each state at time t, compute for each incoming edge okay, the sum of the cost or the reward, depending on which way you're doing it, of the originating state. Originating state means like the state at the other side of the edge. Okay, so each edge, like if you're here, then you're looking at an edge, and the originator is just the state that that edge goes out of. So add that and the cost or reward of the edge itself. So do that for each incoming, so for each edge, for each state at time t, and for each incoming edge, you do this. I guess I'll say 5. Actually, let's make this kind of a sub numbering here. So for each state at time t, do that. Find the edge with the lowest or the biggest, depending on whether you're trying to minimize cost or maximizing reward. Sum. We'll label that edge as the winner. And assign the sum, cost, or reward of the winning edge to the current state. And do that for all the states at time t. Okay, and then if t is strictly less than the time of the end state, then just increment t and repeat. So go to 3, I guess. Okay, so when that loop terminates, okay, you'll have assigned a cost, and you'll have a winning edge for like every state up to and including the end one. So at that point, you just start at the end state. Just follow winning edges all the way back. Back to the start state. That's your path. That's the minimum cost path. Okay, just piece together. So for each state will have one winner, one winning edge coming into it, right? So that's true of the end state. That's true of all of these. Okay, so starting at the end state, just pick the winner of these two. They'll take you to some state. Pick the winner of those two. Eventually end up back in the start state, and that's your best path. Okay, so I'll do an example. I have kind of a pre-constructed example that doesn't end up being degenerate. Hopefully. Yes. Okay, so it's a little bit shorter than that example. So again, when you're doing Viterbi, you don't really care what the labeling of the states is. Okay, all that really matters is the cost per edge and kind of the interconnection pattern of the edges. Okay, so I'm going to do an example with just 4 transitions rather than 5. But I'll use the same edge pattern as in our regular example. And that. Okay, so I'm going to put some costs on these edges here. So 0, 1, 0, 1, 1, 2. And going top to bottom, 2, 1, 0, 1, 1, 1, 2, 0 on this one, 1, 2, 1, 0, 0, 2, 1, 1. This is what I want. Yeah. Okay. So the input to the algorithm, you got to mark the start and the end. Okay, so actually only 4 paths in this one. So you can kind of enumerate them and you can just go through and find the path with the least cost. But let's run the algorithm and see how this works. Okay, so you start at the start state, you initialize that with, we're doing cost here, so we're going to minimize the cost. Okay, so these are all costs. We want to find the lowest cost path, as opposed to these being rewards, and you want the maximum reward. So either way, you initialize this to 0. Okay, and then go to the next stage. For each state at the next stage, you look at all the incoming edges. Okay, and find the winner, label them, and then move on. So we have to worry about these states. They're effectively not even there because you can't reach them. Okay, these 2 states, they only have one edge. So that's kind of easy, right? So thank you. So for this stage, or for this state, okay, you're going to look at all the incoming edges. It only has one. Okay, for that edge, the cost of the sum that's talking about over there is 0. This cost associated with the originating state plus 0 on this one. That's the only one, so that's the winner. So I'm going to hash that as the winner, and then the winning cost goes here. Okay, for this one, it only has one edge. It's this one. The cost is 0 plus 1, so 1. So the cost here is 1, and that's the winner. Okay, move on to the next stage. Okay, so here again you only have one edge. That's got to be the winner. So hash it, and the cost is the sum of the cost on the edge and the cost of its originating node, originating state. So that's 1. Here again, cost is 2. This will get more interesting in a moment. Okay, these also have only one possible way to get to them. So those are the winners, and the cost here is 1. The cost here is 2. Right? Okay, so keep going. So let's do this stage now. So now I actually have competition. Okay, so for this state, I've got 2 incoming edges, right? The cost of this one is 0 plus 1. Cost of this one is 2 plus 1, right? So the 1 wins, right? So that's the winner. Cost is 1. Here, I've got 2 on this side, 2 on this side. It's a tie. I didn't really specify ties. Ties, you just pick one. Pick one of the two. Choose the winner among one of the edges with the lowest sum cost. So it doesn't matter which one you pick. Just pick one. So I'll pick that one. You can pick the other one if you want. Okay. This one, you've got 3 coming from this side. You've got 3 coming from this side. So that's also a tie. So pick one of them. This is 4 coming from this side and 2 coming from this side. So this is definitely the winner. Okay. And then you can do these if you want. They don't really matter. All we really care about is what happens here. So for this end state, if I did this right, we got 4 coming from this side. And I've got just 2 here. So that's the winner. So that completes the loop. Okay, and then the last step is you start at the end and just follow the winners all the way back to the start. Like that. So there's your minimum cost path. Okay, in this case, you can just run through all 4 paths, and you'll see that indeed 2 is the lowest cost you can get. Okay, so if this were an instance of this problem here, where all of the costs on the paths correspond to numbers of bits, okay, that would say that this path through the trellis is the maximum likelihood estimate of what the encoder did, and moreover, we're guessing the channel flipped 2 bits. Right? And actually, there's no path here with a cost of 0, so the channel had to flip something. Okay, and it's basically looking for the path that results in the fewest number of flip bits, and this is it with 2. It's sometimes useful to do this with rewards rather than costs. So you set this thing up where you have these numbers represent good things rather than bad things, and you want the path that accumulates the most good things. So that's a very similar algorithm. You just take for the winner, you just take the larger of the 2 rather than the smaller of the 2, and the rest of it's all the same. You can just view cost as minimum reward, like negative reward or something like that. Yeah.
At the end of last lecture, you quickly mentioned that the cost-based analysis has the underlying assumption that epsilon is less than 1/2.
Yes.
Could you talk about that just a little bit more?
Sure. So that comes about from when we did the map calculation. So it's like you good with that? So for this particular channel, we said the conditional PMF is this. Yeah? Okay, so if I want to find the x, I don't care about the largest value of this. I care about which x achieves the largest value, right? So as such, I don't need this factor, right? Because it doesn't depend on x. It's just, let's say multiply everything by 2. I mean, it's not going to affect which x gives you the largest value, right? Okay, so now if epsilon is less than 1/2, then this thing is less than 1, right? So if this thing is less than 1, then a way to maximize this thing is to minimize that, right? So you want to find the x that's a valid path that's closest to y in terms of bit flips, if epsilon's less than 1/2. If epsilon's bigger than 1/2, then this factor is bigger than 1. So you maximize this thing over x by maximizing that. So then you want to find the x that's farthest from y. Because the channel tends to flip bits. So if it didn't, consider the channel as a hypothetical channel that flipped every bit. Okay, so then you want to find the x that actually differs from y in every bit, right? Yeah. I mean, it's kind of a weird thing. I mean, in practice, like I said, if your epsilon's bigger than 1/2, you would just redefine 0 and 1 at the decoder. Just swap the labels, right? And now epsilon's less than 1/2. So it's the more reasonable case. But mathematically, that's the way it works out. Okay. People clear on the algorithm, like how it works, how to implement it? Think you could program it at this point? Okay. I'm not going to write out a proof that this indeed is the minimum cost path. It's not too hard to see it, though, if you just sort of stare at it, what it's doing. Okay, so the way you'd show it is by induction. So you just show that, at each state, once you've chosen a winner, you've found the minimum cost path from the starting state to that particular state. Okay, and you just show that by induction. So that's clearly true, here, right? I mean, this first stage, you only have one arrow coming in. There's only one possible path to the start, so that must be optimal. Now, if it's true, up to time t minus 1, okay, then look at a state at time t, right? So suppose I want the minimum cost path from the starting state to here. Well, it's got to come in one of two ways. It's got to come in either that way or that way. There's only two possibilities to get to this state from the start, right? Okay, now, if it comes in this way, it would have to follow the minimum cost path to this state and then just tack that on, right? It wouldn't go some other weird way and then tack this on because we've already assumed that the path to this is the minimum cost path to this, right? Okay, so if the minimum cost path to this state goes through this edge, it must follow the minimum cost path to this state with that one then tacked on, likewise here. Okay, so then you only have two possibilities left now. You look at the minimum cost path to this one with that state, minimum cost path to this one, followed by that edge, sorry. So minimum cost path to this state followed by this edge, or minimum cost path to this state followed by this edge. You only have those two possibilities to compare. So you compare those two. Okay, this number here is the cost of the path from the start to here. This number is the cost from the start to here. Okay, so you just compare those two and that's it. Okay, so at a high level, that's the argument. And this is useful more generally. I think it was first developed in the context of this kind of a problem. But in general, whenever you want to find the minimum cost path through, I guess it's a directed acyclic graph, right? It's a directed graph with no directed cycles. And you want to find the minimum cost path between two states. Like this algorithm will do it for you. Yeah?
I think I'm having a little bit of trouble with the amount of abstraction that we're kind of here.
Okay, yeah.
Once we have this minimum cost path,
Yep.
we have the trellis, then we can highlight that path.
Yes. Yes.
How does that help us with a better decoder?
So that tells you why does it give you a better decoder?
What's the aim for that? I understand the algorithm. I understand all the pieces.
Okay.
I'm having a hard time.
So did you see how to get the data bits
Yeah.
from this? Once you have the path, you can get the data bits from that, right? So once you have a path like that one, then you would highlight that as a path here. So let's suppose it was blue, orange, green, blue, blue, right? So then go back to this form of the diagram, okay? And then I forget which direction I did here. I did this one, right? So, and this diagram, you have the input bit, right, associated with each edge. So you know that the input to the encoder was 1, 0, 0, and then you have these two dummy zeros after that. So you can can pull it off. You can pick off the input then from a path. Yeah, once you have a path, every path corresponds to an input. And once you have if you have an input, you can certainly get a path. That's just implementing the encoder. And once for any path, if you draw it like this, you can then pick off what the input was. So if a Viterbi algorithm gives you a path, it's the maximum likelihood path. And then from that path, you can get the U bits. OK, other questions? All right, so this is useful much more generally, but we'll use it mainly for decoding convolutional codes. I mean, it's a general kind of graph theoretic algorithm for computing minimum cost paths. How do you generate the cost online for a specific thing? Are you asking how do you get these numbers here?
Yeah.
That you put in like how do you get these numbers? Not static, right? So once you have y, then they're set, right? So so if you ignore these costs for a moment, like the colored edges, that's fixed, right? That's part of the code, right? So that's like hard coded in the encoder and decoder, what all these strings are here, right? Once you get a y string, okay, then you can put that at the top, and then for each edge, you can say, okay, so we know we got a 1, 0 here. So if the encoder sent a 0, 0, then that would have there would have been 1-bit flip. Whereas if the encoder sent a 1, 0, there'd be no bit flips. And you do that for each edge like that. And then you have costs for each edge, and then you run Viterbi. Yeah? OK. Other questions? All right. So that's for the binary symmetric channel. What about other channels, like ComCloud? OK, so at a high level, there's sort of two solutions to this, two angles. So the simplest of the two, is to use something called hard decision decoding first, and then run Viterbi. OK, so let me explain the way this works. So suppose you have a channel, and it's not a binary symmetric channel. It's some complicated thing. It's ComCloud. OK? So what you can do first is just design an encoder and decoder for it without using any of these ideas, just using PAM and stuff, like your Lab 4, basically. So design a communication system using something like Lab 4. OK? This now, here's the power of abstraction. OK? Look at this end to end. I feed bits in, I get bits out. Some of them are flipped, right? That sure looks like a binary symmetric channel, right? I mean, OK, BSC assumes the bit flips are independent. You know, with your Lab 4, the bit flips may not be independent. If one bit is flipped, it's possible. Maybe it's actually likely that neighboring bits will be flipped, but you know. You can really just treat it as a binary symmetric channel, right? Just take your Lab 4 and then view the bit in, bit out object, okay, that you get by encapsulating the channel in your encoder and decoder. Just view that as a BSC, okay, and then just wrap your convolutional encoder and decoder around that. So actually, I'll put Viterbi decoder here. Okay, so you just tack it on the outside. Okay, so design your Lab 4 first. Okay, once you have that working reasonably well, it might have a really low error probability, but once it's working reasonably well, okay, then add these boxes to it. So take the actual data bits you want to send, first convolutionally encode them to get a longer string of bits. Feed that into your Lab 4. So your Lab 4 needs to be able to handle like variable numbers of bits with a longer string. Okay, so you got to work that out. Okay, let your decoder come up with a guess of what the bits were over the channel. Okay, and then feed that into Viterbi and allow Viterbi to try to correct some of the remaining errors. Okay. So let's call this the the base system. If the base system is rate R bits per second, and the convolutional, let's say R1 bits per second, and the convolutional code is rate R, where R is like the, remember the I divided by theta. Okay, so R 1/2 means that each data bit gives rise to 2 output bits. Then the overall rate will be the product of the two. Okay, so in particular, if you use the example convolutional coder I had that takes in 1 bit and spits out 2, okay, if you use that code with this design, okay, you have your data rate, right? Because this base system was operating at a certain data rate. Let's 10 kilobits per second, let's say, right? Okay, now if you include this thing in here, like each bit here gives rise to 2 bits here, right? And this ends up being passed at like 10 kilobits per second, right? So this, the actual data rate that this is experiencing is going to be 5, right? Because this is accepting bits at rate 10 kilobits per second, and this is kind of doubling the bit rate here, okay? So if you do this, you have the data rate. Okay, now the hope is that you'd also be more resilient to errors. You could recover from errors better than you could before.
Doesn't it half your effective data rate, though?
As opposed to what?
Like you're putting in 5 bits and it outputs 10 bits. Even though it's like doubling the rate, doesn't mean that you're giving more information at the same amount of time.
So for a convolutional code, we define that as rate half, not rate 2.
Yeah, okay. So it's the inverse of it.
Yeah, so the inverse of it. So exactly. So if this thing is 10 kilobits per second, and I use the example convolutional code I had that took 1 bit and spit out 2, then R is half. So I'm halving my data rate, yeah. That's why we define the rate of the convolutional code the way we do, actually. It might seem like the reciprocal of what it should be, but this is why, right here. So lower rates are bad because it means that the bits here blow up into a lot of bits over here, which you then have to send at the same rate you were sending bits before. Okay, I think we're good with any questions about the trellis? I'm going to erase it at this point. Okay, the second option they call soft decision decoding. Okay, so this works if each bit in X I'll say corresponds to, the language is a little bit vague, but corresponds to one sample in Y. Okay, so what you can do, rather than having the decoder make a hard decision on each bit first, and then having the Viterbi decoder try to go through and correct errors afterwards, you can try to combine these two and sort of run Viterbi directly on the channel output. Okay, and this can be useful because there might be, let's suppose in your channel, this is a Gaussian channel, you're doing antipodal signaling. Okay, so for a particular input, for a particular output, the received amplitude might be quite near 0, right? And then if you do this hard decision decoding, what's going to happen is your decoder is going to say, oh, it's slightly bigger than 0, so we round it up to 1. And it reports to Viterbi that was a 1. Okay, but in doing that, you've just given up a lot of information, right? You weren't really sure about that bit. And now you're pretending to the Viterbi decoder that you were quite certain it was a 1, right? It'd be better if you sort of somehow conveyed to Viterbi, we're not really sure about this bit. Okay, so don't put too much stock into it. Okay, so you can basically just run Viterbi kind of directly on the channel outputs, assuming things line up well so that the Y's and the X's line up the way they did in the binary symmetric channel. So okay, so that's true in general, valid path okay, so if your channel is, like independent over the y symbols, and each y symbol kind of corresponds to one bit from the convolutional encoder, okay, then this we can write as a big product like this. Okay, and it's helpful here to take logarithms. Okay, since we just want to know which x gives rise to the maximum, I can apply any monotonically increasing function I want to this thing, right? And it won't change which x achieves the maximum. It'll change the maximum value, but not which x gives me the maximum. So we take logarithms. That turns the product into a sum. Like that. Okay, so this you can solve by just finding a max reward path through the trellis. Where the reward is just given by this log likelihood. So for one particular edge, instead of looking at like the transmitted bits on that edge and the received bits on that edge and marking how many bits they're different, okay, just take the received bits, take the transmitted bits corresponding to that edge, plug them into the channel likelihood, take log of that, and just put that number on the edge. Do that for every edge, okay? And then find the maximum reward path through the trellis, and that will be the map estimate. Okay, so this in general will do better than hard decision decoding, okay, because you're not losing as much information. You're using actually using the channel outputs to decode. Okay, so I have just like kind of like 3 short points about convolutional codes to make. I don't know if we'll squeeze them in, but I'll do 1 or 2. Okay, so that's the basics of convolutional codes. One limitation with the way we've done this, okay, is that if I equals 1, i.e. the number of different shift registers is 1, okay, then the rate must be of the form 1 over theta, where theta is a positive integer, right? Now if you have 1 shift register, okay, then each time step you're going to feed in 1 bit, and you're going to get some number of outputs depending on how many taps you've got, right? Generally at least 2. Okay, so the rate has got to be of the form 1 over the number of taps. Okay, in general, we define the rate to be the number of different shift registers divided by the number of taps. Okay, if you only do 1 shift register, okay, which people often do in practice because as you increase the number of shift registers, the trellis really blows up. Okay, state space blows up exponentially. Okay, so if this is true, then your rates are of the form 1/2, 1/3, 1/4, and so on, right? In particular, they're quite low. All right, so it's like if you do this, then to apply the idea at all, you have to take at least a 1/2 rate hit, right? Like the best you could hope for would be a 1/2 rate hit. Maybe it's even worse, it's a 1/3 or a 1/4 or something. That's potentially a rather big cost to incur, right? You're halving your rate just to bring this idea into play, all right? So a way around this is to use multiple shift registers. So you can use I bigger than 1. Okay, the issue with that is that it can make the decoding rather complex, so the trellis really blows up. At each time step, the number of different states you've got in the trellis is like 2 to the power number of flip-flops in your system overall, right? Okay, so like you add a shift register, you bring in like 3 more bits, okay, and you multiply the number of states by 8 or something, right? So I mean, the thing blows up quickly. You just start adding shift registers. Okay, so in practice, people don't really tend to do that. What they do is they stick with I equals 1 and they puncture. Puncturing is quite simple. You just omit certain bits from the encoder's output. I.e., you don't send them. So they'll be produced by the convolutional encoder. But just don't send them. So very quickly, so here's the example we had. Like that, right? So it's like, each bit that comes in would give you 2 output bits, right? So I mean, let's keep things simple. Suppose you're just encoding all zeros. If you're encoding all zeros, you're always going to get all zeros at the output because it's linear, right? So you, at each time step, you would get 2 bits, right? So let's just write it this way, right? So each input bit gives me 2 output bits. Okay, let's not rush this. I'm trying to squeeze this. It's never a good idea to squeeze it in at the last minute. Never a good idea. Okay, so I'll do this. I'll do this properly on Tuesday, I guess. Okay, so we have just like, I don't know, 10 minutes left of convolutional codes. So on Tuesday we'll do this. I'll put up the standard, the Wi-Fi standard. I'll show you the convolutional code that they use. It's all the diagrams. You'll recognize the diagrams. They're all in there. I'll talk about turbo coding very briefly and how it's connected to convolutional codes. With that, we're done with coding. And we'll do wireless from here on out. Okay, so office hours now, if you want to chat about homework or whatever. Otherwise, I'll see you Tuesday. We got lab, I guess it's lab 2, I guess, back from the grader. It's kind of late, I guess. Sorry about that.